Can be kind of loud sometimes.
All right. So the next problem. So are we ready? Cool to go to the next one, Fred? All right. Yeah, so this is the problem where we can actually calculate the mutual inductance. In very few configurations can you calculate the mutual inductance. Okay, so here's a problem where we can calculate the mutual inductance. So a coil of 40 turns is wrapped around a long solenoid of cross-sectional area 7.5 times 10 to the minus 3 meters square. The solenoid is 0.5 meters long and has 500 turns. What is the mutual inductance of the system? The outer coil is replaced by a coil of 40 turns whose radius is 3 times that the radius. What is the mutual inductance of this configuration? Okay, so let me do a drawing first. So here is the solenoid. Okay, and around this solenoid is a secondary coil wrapped around. Okay, so there's the secondary coil, and this is part A. For part B, I'll draw the diagram again. For part B,
Same concept of turns.
no, the outer coil has a bigger radius, that's all. Okay, same thing. And what you'll see in a second is the mutual inductance for both these configurations is the same. Okay, so let me write down the defining equation for a mutual inductance. Okay, so you saw that a second ago. EMF in the second coil is equal to negative M12 di1 d2. Okay, so in our notation, this is coil 1, this is coil 2. Okay, so what's happening is this is the coil that's hooked to a battery or a source, and that's you're providing a current in here. So you could connect it to the wall. You're providing an AC source here, and because of the changing currents in this coil, you're inducing an EMF in this coil. Okay, and how do you induce an EMF in that coil? Okay, so what is happening is every time you have a current here, you're producing a magnetic field in this coil, and that magnetic field is threading the second coil, and anytime this magnetic field changes, there is an induced EMF in that coil, in the secondary coil. And how do you change this magnetic field? You either change the current, or if it's an AC current, this magnetic field will be flipping back and forth. Okay, it doesn't matter how you change it, but as long as you change it, you're inducing an EMF in there. Okay. All right. Mr. Faraday will tell you that the EMF induced in the second coil is equal to the rate of change of magnetic flux through that coil. Okay. Now, what was I looking for? The flux through this secondary coil is, now the property of the solenoid is that it produces a magnetic field, a strong magnetic field, uniform magnetic field inside the coil, and outside the coil the magnetic field is 0. Okay. So here's a solenoid. The coil field is only in here. Outside is 0. So if you have a coil outside, the flux threading through that is just in that area. It doesn't matter what the size of the coil is, the outside coil is. Okay. All right. So just keep that in mind. Okay. Now the magnetic field inside a solenoid So is given by, I'll call it B1 because it's in coil 1, mu naught N1. N is the number of turns, and all subscripts 1 correspond to coil 1. All subscripts 2 will correspond to coil 2. Okay, I1. Okay. So, and now, oops, so I need another page. All right, so now let's go back to the EMF in is the flux through the EMF in coil 2 is the time rate of change of flux through coil 2, magnetic coil 2. Okay, we'll give it that. Okay, but this is equal to, the flux is d by dt of B1 A1. The flux through coil 2 is just the flux, the magnetic field through coil 1 times the area of coil 1. The area of coil 2 does not come into play at all. Why is that? Because the magnetic field is only in this region. Okay? And I've chosen to draw the direction of the magnetic field, but it could be the other way as well. Okay? All right, so let's go back to this, and this is equal to minus d by dt of mu naught N1 I1 A1. Okay. Now in this thing, the only thing that will change is we are not going to change N1 A1. The only thing that will change is I1. Okay. If only when the current in this coil changes, that's when the flux through this thing will change. Okay. So that's the only thing we're going to change. So mu naught N1 A1 d by dt of I1. So this is from Faraday's law. So according to Mr. Faraday, okay, and here's the defining equation for mutual inductance. And so if you compare these two equations, you can see that M1, the mutual inductance for the two coils is N1 A1. Okay. Mu naught times N1 is the number of coils in for coil 1 and area of cross section of coil 1. Okay. And that's true for both cases, for A and B.
This outer coil isn't getting a current, right?
I'm sorry?
The outer coil isn't being fed a current via electricity. It's just literally a coil of wires around this all.
Okay, so we don't care what is connected to outer coil. What we are telling you here is you could have connected 100 batteries to outer coil. In addition to those, you're getting this EMF from changes in coil 1. Now your problem is to think if this is going to mess you up for whatever it is that you're trying to do in coil 2. Okay, so you have to be cognizant of this fact, this voltage. And in the previous problem you saw that that voltage can be quite high. What was the maximum value in the previous problem of that voltage? 320 volts. Okay. All right, so for both A and B, this is what do I need to do? Add a page below. Okay, so for both A and B M12 is mu naught N1 A1. Okay, so it depends on the dimensions of A1 of coil 1. So now we'll calculate this. Mu naught is 4 pi times 10 to the minus 7 Tesla meter divided by amp. N1 is the number of coils per length for the first coil. It's got 500 turns divided by half a meter. Okay. See, 500 turns and length of half a meter. Okay. And area is 7.5 times 10 minus 3 meters squared. And area is 7.5 times 10 minus 3 meters squared. And so all those units combined to give you henries. Inductance is measured in henries after Mr. Henry. And let's take care of powers of 10. There's a minus 7. So that's we'll borrow 3 actually, and that will cancel that. So 3 from here, 10 to the 3, so that becomes 10 minus 4, and then you get a 3 again, 10 minus 7. Okay, so you have 10 minus 7 henries, 4 pi times 7.5. Okay, and so this is according to our friendly calculator. This is 9.4 into 10 minus 6 henries, or 9.4 microhenry. So that's the mutual inductance. Okay. And again, why do we care about this number? So now that you have calculated this number, so in both these configurations, if you have a secondary circuit in a configuration relative to the first circuit like this, what this is telling you is here's 10 microhenry, that's what we calculated. As you change the current in the first coil, that's the EMF induced in the second coil. That is the multiplicative factor. Okay. So for this to be significant, you'd have to change the current quite fast here. Okay. That's what this tells you, because this is 10 millionth of a henry. Okay. That's the factor we calculated. All right. If Fred and anybody else do not have any questions, we'll go to the next one.
So we don't have the same answer
For A and B, yeah, because the mutual inductance didn't depend on the area of coil 2. All right.
What's the point of giving us the number of turns in coil 2? Yeah.
Whoa. There is.
There is?
Yeah. So, all right. So see, that's why I asked Fred, do you have any questions? Okay. The coil of 40 turns is wrapped around so here's where I made the mistake. Okay. So this is that, and this flux is N2, the number of coils in that's the total flux going through coil 2. So N2 has to come in. N2 is the total number of coils. N2. So everything we said, you just multiply N2. Okay. and N2 was 40 turns. Okay, so multiply everything by 40. Oh, why did you not notice that earlier, Fred?
Because I remembered because I did the homework for 14, I remember seeing something like this. I was like, I couldn't remember what it was that was off.
All right, 376 microhenry. All right, so let's go back and point this out again. Okay, so what is it that we left out?
Oh, wait. We already had a coil of 40 turns. No, the solenoid is 500. Yeah, the solenoid didn't change. It said the outer coil changed. The outer coil, the outer coil radius changed, but the number of turns stayed the same.
But we
But we didn't
number it
multiply to the
ever.
end. Oh, okay. That's a problem.
All right, so everybody understand? Okay, again, let me go over what we are saying here. Okay, so here's here's the mistake I made. Well, okay, so this flux is threading through that. The total flux through that depends on the number of turns of this coil. Okay, so I initially wrote the coil through assuming this was only one turn. I'd forgotten that it was 40 turns. Okay, so the total flux through there was the number of turns in the secondary coil times B1 times A1. Okay, let me, just a second, Ben. So this is N2 B1 A1. So, okay,
And that's the equation for flux.
that's the equation for flux. Yep.
So the area of the solenoid does not matter.
The area of the second solenoid does not matter. Right. Okay, because why doesn't it matter?
Because all of the magnetic field is contained
Within the solenoid. The solenoid is a device such that it produces only a magnetic field within it, and outside the field is zero.
And the strength isn't affected by that getting wider or smaller. Yeah.
Yeah. So if there was a field outside, then the outside coil area would matter. Okay. Yeah.
So it's giving us the radius just to tell us nothing.
Well, the point was the second,
To show that it has no.
yeah, it has no effect.
Okay, very good.
All right. All right, on to the next one.